So the last stage is the statistical tests. So you have tests for difference and you have tests for relationship. The tests you'd use to measure difference would be the dependent t-test or the independent t-test, and the tests for relationship would be the Pearson's test and Spearman's test. The point of these tests is to establish a statistical significance within your data, and it basically just establishes how significant the relationship or the difference is. Now, it's really key here that you notice that this is only statistical significance. A test might prove that your data doesn't have has no statistical significance. However, it might still have practical significance. For example, if you were to look at sprint times, then the results may show no statistical significance. However, there may have been a difference. Everyone's scores may have improved by half a second, and that shows extreme practical significance. So you need to understand that whilst there may not be statistical significance, practical significance is also very relevant and something that could be discussed in a research project. To determine which test you would use, you would look at what is called a decision tree, and I'll show you an example of that. So there are many factors to account for within that decision tree, so whether it's difference, relationship / correlation, whether it's normally distributed or not, the level of data you have, so whether it's nominal, ordinal, continuous, whether you're looking at two or more factors, whether you're looking at one factor, and yeah, you can see that all displayed on the decision tree there. And when you're establishing statistical significance, you'll use what is called a critical values table, and this will be dependent on the test you use. The critical values that you use will be dependent on what test you're using, what hypothesis you're using, but I'll show examples of that as I go along through the tests as well. So the first test is the independent t-test. So like I said, this would be a test of difference. So you can see the formula for an independent t-test at the top there, and breaking that down, basically M is a mean and SD is a standard deviation. So we've got a worked example here, and this is based on static sprint between two different groups, basically. So static sprint scores for group A and static sprint scores for group B. So you have the raw data there for both of those groups, and then I've established the mean for each of those groups. So the mean for group A is 2.36143, and the static sprint for group B, the mean for that was 2.497. Standard deviation, again, I've done that for both groups. So standard deviation for group A is 0.23366, and standard deviation for group B is 0.282. So if we put that into the formula, start breaking it down a bit, you've basically got mean 1 minus mean 2 at the top of that formula. I'm putting that to use on the data that we have already. So you've got mean 1, which is the mean that I took from group A, and mean 2, which is the mean that I took from group B. So mean 1 minus mean 2 resulted in minus 0.13557. So that was the first mean minus the second mean. I then moved on to do the lower half of the formula, or equation, sorry. So you then go on to look at the standard deviations. So again, you've got them separated into standard deviation 1, standard deviation 2. Standard deviation 1 is going to correlate with the mean one, meaning they are both representative of group A, whereas mean 2 and standard deviation 2 are representative of group B. Similarly, you have N1 and N2, N just meaning the number of participants. In this case, there was 14 for both groups, therefore both N1 and N2 are 14. Putting that into the calculation then, so you've got 0.23366, which was the first standard deviation, and you square that to get 0.054597. You then divide that by 14, as it was standard deviation 1 squared divided by N1. Dividing that by 14 gives you 0.00389979. Working with long numbers, but just for this case, just to show you how to work through it fully. You do the same again, but obviously for the second set of data. So in this case, you've got a standard deviation 2 squared over N2. So in this case, you've got 0.282 squared, which equaled 0.79524, and then you divide that by 14 again, because you've got the same number of participants, and that equals 0.00568029. Moving on to the next stage then, you add those two numbers you just achieved. As you can see that in the equation, you add those numbers. So obviously we broke those down, worked out each of those individual sides of the sum before, and now we can add those up. So we achieved 0.00389979 for the first half of the sum, and we're adding 0.0056829 to that, and that will equate to 0.00958008. So that's the bottom half, almost complete. Of course, there is a square root over that, so we will have to square root that number, and the square root of that number results in 0.097877883839. So that's the bottom half of the equation done, and we've already completed the top half of the equation prior to that. We already did mean 1 minus mean 2, so now it's just doing the top half of the equation divided by the bottom half of the equation. So there, putting that into action, we have 0.13557 divided by that 0.09787, and that equates to 1.3852048. I rounded that up to 1.385, and then that means that t equals 1.385. There was no significant difference here, as I calculated 1.385, that was my calculated value, and the critical value in this case is 2.101, and I'll go into more detail with that when discussing a dependent t-test, as I have the critical values table alongside that one. Before I move on to the dependent t-test, actually, I need to differentiate between the two. So the independent t-test is used when normal distribution is assumed, and you have two data sets or measures from two different groups of participants. Dependent t-tests are used when normal distribution is assumed, and you have repeated measures data. So that means it's from the same group of participants. Same participants are used for both. So you can see here, same participants been used. It's a pre and post recording for standing vertical jumps that have been used. So same group of participants, just different times. Repeated measures, same measures, as it's the same test. So again, the equation can be seen on the screen now, so top right, and the workings out are displayed below it. So in the table, you've got participants, standing vertical jump, pre-test and post-test, and then difference and difference squared. So d in the equation is difference, and obviously d squared is difference squared. And you also have the total and the mean, just to make it clearer for myself. So I'm going to start off by looking at the total difference. In this case, that was -6. So -6 would go at the top of the equation. You also look at the total of the difference squared, which was 10 as well. So the reason you need the total difference squared is for the lower half of the equation. So you've got n is the sum of d squared in the first bracket. N is 14 in this case because we have 14 participants. So you do 14 times 10 because 10 is the difference squared, which we just looked at, and that results in 140. You then do the other half of that top bit of the lower half, I suppose. So the sum of d squared, which is -6 multiplied by -6, obviously, because it's -6 squared, because the total difference was -6, and that results in 36. So obviously that in the equation you've got n times the sum of d squared minus the sum of d squared. So therefore you do 140 minus 36, which equals 104. Lower half of the equation, the bottom bit, you've got n minus 1. N minus 1 is 13 because 14 minus 1 is 13. Then it's pretty simple from there. You've got the lower half completed practically. Just got to do some division and square rooting. So you've got to do 104 divided by 13 because you've got the top half of that lower bit divided by the bottom half, and that results in 8, and then you have to square root that. So square root of 8 is 2.83. Then you've got that previous total difference that was at the top of the equation, which is -6, and you divide that by the number you just achieved, which is 2.83. So -6 divided by 2.83 results in 2.12. So t equals 2.12. And this is where the critical values table comes into play. So this is the critical values table for this test. And this is basically how you determine how significant your findings are, how significant your t-value is. So in this case, you've got to, for DF, you've got to look at n minus 1. That is the rule for this table. And n minus 1, so we had 14 participants, therefore DF will equal 13, because 14 minus 1 is 13. So you look down the DF column on the left, down to 13, and then you'd go along to 0.05, because we're looking at the level of significance of 0.05 for a two-tailed test. So you go along and find that your critical value is 2.160 in this case. And if your calculated value is more than your critical value in this case, then that would show a significant difference. Our calculated value is 2.12, which is less than the critical value, so there is no significant difference. And that is how the critical values table works.